Probability of finding life beyond Earth, if you don't look for it, is zero. SETI makes sense if there are, in fact, large numbers of advanced technological civilizations out there. Then how long do they remain detectable? The most remarkable thing we may discover about life is that it's not remarkable at all.
You're the CEO of the SETI Institute, which is where we're at today.
Yep.
Can you tell me what the SETI Institute actually does?
Sure. Well, the SETI Institute is a research and education and outreach organization. SETI is an acronym which stands for the Search for Extraterrestrial Intelligence, and it's actually not even correct in a sense, because what we're really doing in SETI endeavors, which is part of what we do here at the SETI Institute, is we're looking for extraterrestrial technology. We're looking for evidence of technologies or phenomena that we can observe from great distances that are clearly not natural in their origins. And this would serve as a proxy for life and intelligence. So it's really an endeavor to look for artifacts in the cosmos that would suggest the presence of an intelligent technological species somewhere beyond our solar system. At the same time, the SETI Institute's research over its 4-decade history has broadened into the full spectrum of what we now call astrobiology, which is, broadly speaking, the study of life in the universe. And so that means looking at everything from the origins of life and the conditions under which life exists to the evolution of living systems from single-celled molecules and single-celled living species to complex species, ultimately intelligent species, and then eventually technological species. So we cover the whole spectrum. And then we also do education programs which really leverage, I think, the kind of fascination that people have with science and aliens and astronauts in space to, bringing better science literacy, more fun ways of learning and teaching science to bear on, teachers, students of all ages, and then outreach programs to do the same for the public.
What does SETI and the search for extraterrestrial life actually look like in practice?
If we talk about broad SETI, or therefore astrobiology, there's 3 ways to look for life in the universe. There's what we call in-situ, which means sending hardware to the place of interest. And that's what we do with rovers and other spacecraft or landers that go to a place like Mars, or will go to a place like Europa, or to Venus, or Titan, and look for signs of biology, of living things, or evidence of past living things on those places. The next way to look for life is what we call remote sensing. So this would be using observational platforms, usually space-based platforms, to look at planetary systems and look for other evidence of life that might be on the surface. That could be just features and phenomena in the geography or topography that we might observe in places like Mars. But now with the James Webb Telescope, it also includes the ability to look at the thin veil of atmospheres around planets, around other stars, not in our solar system, and evaluate or characterize their atmospheres. And therefore we can look at and look for so-called biosignatures. We can look for atmospheric compositions that would be difficult or impossible to explain without the presence of life on the surface of some sort. So that's called remote sensing. That's extraordinary. In situ is good for our solar system, because right now we don't have the technology to get beyond it. Remote sensing is good for about 20 to 30 light years, depending on the size of the planet and so forth. That's about how far we can do spectroscopy with James Webb.
Which is still crazy, because you think about the Kepler telescope from 2009, right? And how they didn't even think that the technology could exist to look for exoplanets around stars.
That's right.
And now not only do we know that the exoplanets are ubiquitous, right? But now we can use James Webb to look at the atmosphere. Yeah. That's crazy.
Well, think about this in the context of SETI. So SETI, the Institute, started in 1984. The endeavor started with Frank Drake's first experiment in 1960. So for all of that time, until the first discovery of exoplanets in the mid-90s, and really the Kepler mission in 2010s, did we even know that there were planets? So up until then, we didn't know. So we were doing SETI on an assumption, right? I mean, of course, astronomers, I think, had a pretty well-informed sense that there must be planets, and we just, don't have the technology to find them or see them. And we don't necessarily know yet how they're formed. We kind of do now, but nevertheless, we believe they must be there. So this still means that we were undertaking this endeavor, this search, without knowing that we have a target to search for.
Right.
And now, of course, we do.
They're like, let's just look. See what's out there.
Exactly. So that's James Webb. That takes us, about 20 to 30 light years out. And bear in mind, the Milky Way galaxy, and you know everything about galaxies, you know more about galaxies than I do, is 100,000 light years across. So, 20, 30 light years isn't very far, even though it's impressive technology. SETI, as an endeavor where we look for evidence of radio and or laser technologies, non-natural phenomena, usually based on the manipulation of the electromagnetic spectrum in some way that is not natural. Those can be manifest across the galaxy.
Right.
And so we can see those, the parameter space, if you will, is enormous compared to remote sensing or in situ. So we're involved in all three of those endeavors. We support missions that NASA does that go to these planets. We're a big part of the exoplanet mission, the Kepler mission. We did the data management for that mission and the data analytics. And then we, of course, do SETI. And the SETI work is done primarily with radio telescopes. And we have our own radio telescope array called the Allen Telescope Array in Northern California. And we also have a project on the Very Large Array in New Mexico, where we are doing what we call commensal observations, which means piggybacking. Whatever they're pointing the telescope at, we capture everything that they're looking at, the so-called field of view, and we process that for SETI signals.
Allen is looking at specific things,
Allen
right?
Telescope Array is still somewhat of a survey instrument in that it has a wide field of view, but we can point that at very specific targets. In the Very Large Array, we can also point at specific targets because we can do what's called beam forming. We put these electronic beams on the sky that allow us to target individual spaces. So we can also target there. But yes, with Allen Telescope Array, the beauty of owning and operating our own functioning array telescope is that we can point it wherever we want, whenever we want. We had a paper jointly published with Oxford University in Nature Astronomy about the first ever observation of a gamma ray burst. I think it was the brightest of all time gamma ray burst, or so-called BOAT, brightest of all time. But when this was announced in the astronomical literature, we were quickly able to point the telescope at it and say, well, let's look at it in the radio spectrum. And we, did this analysis that had never really been done before. So that's the advantage of owning your own telescope.
Yeah, it's like the best ship is the one that you steer yourself, right?
There you go.
So have we found anything? I feel like that's the question that everyone wants to know.
Sure. Well, I love that question because I always give the same answer.
Okay.
And the answer is, if we had, you would know.
But then the next question that people ask is, well, is the government covering it up?
People will ask us sometimes, like, if you do discover something, will the government cover it up?
I actually had that question.
Yeah,
so.
yeah. So, well, there you go. And well, the answer to that is we're not a government agency, and the government doesn't even fund the work we do in radio SETI.
Okay.
They fund a lot of the work we do, mostly through NASA. But SETI specifically, Congress decided in the early 90s not to fund anymore. Now that NASA itself discovered that planets are everywhere, they're kind of getting back in the business, funding so-called Technosignatures research. But at this point, SETI research is privately funded, so the government has no ownership of the data. They have no control over what we do. And as far as we know, they're not spying on us, such that if we found something, they'd come and shut us down. Although I sometimes jokingly say to people, if you're worried about that, surround our building with video cameras. And if you ever see a bunch of black Escalades pull up with, gents in their suits and earpieces, you'll know. So even then you won't be able to hide it. If we make a discovery, the first thing we will do is look to other observatories to verify and double check. And then we would, in as dry a manner as possible, just share with the public what we've observed. And we wouldn't jump to conclusions about what it means, but we would say, this is what we've observed.
Now, of course, people will jump to conclusions.
Yes, they will.
Okay, so Contact is my favorite movie of all time.
It's a great movie.
I'm just giddy to be here today. But in that movie, right, if people watching haven't seen it, the search is funded by a corporation, right, or a billionaire. But then the government wants to take it over, right?
Yeah.
So is that just not something that could happen? Like, are there firewalls in place?
Well, one could argue that a government can do whatever they want, that they have the power to do. Would they be motivated to do that? There's a lot of second-order questions associated with the question of, or the discovery of, like a signal or a phenomena. Well, what was it? What is it? What is the nature of it? Does it appear to have information, or is it just a technical phenomena like a laser beam or something? Right. Does it have structure and content? It's not believed that we would have any ability, at least in the near term, to translate, although we're working on the kind of technology that might allow us to do that. But, the other question would be, how far away did it come from? Is this a nearby planet? If it's something, within 10, 20, 30 light years, theoretically, we could have a conversation.
Theoretically.
Right? If it came from 50,000 light years away, we don't even know if the planet still exists
Right.
that transmitted this signal. So, there are so many other questions that, the idea that somebody would swoop in and shut us down, be, well, why would you do that? For what reason?
What reason, right? We answered one question to open up 1,000.
Right, exactly. And we would hope, that the expectation, and I think this is based on statistics, is that if we find evidence of another advanced technology, they've been around a lot longer than we have.
Right.
Because, the probability of two 100-year-old technologies, that's how old, electromagnetic technology is on this planet, discovering each other is like zero. So the longer a civilization has been out there transmitting in one way, shape, or form or another its existence, the greater our chances of discovering it. So that means, if we discover such a thing, they're likely to have been around a lot longer than we are. Therefore, they're a lot more advanced than we are. They'd probably solve the problems we have, which means they don't need anything from us. But it'd be wonderful to think that they might teach us how to survive our own technological adolescence, which right now is a bit of a challenge.
It absolutely is. So all of your work is kind of focused around this Drake equation.
Yes.
Can you tell us what the Drake equation is and how it's central to everything that you guys do?
Sure. The Drake equation is what we call a roadmap for astrobiology. It wasn't intended that way. That wasn't its original purpose or how it even came about, but it functions that way within the Institute. And what the Drake equation is, Frank Drake and 9 other scholars and researchers were asked by the National Academy of Sciences to come together in 1961 and talk sort of scientifically and philosophically about this question of SETI. Does SETI as an endeavor make sense? The reason for that was that, this is something new and interesting, but is it legitimate science? They kind of, National Academies set the agenda for science in this country, so they wanted a perspective. So Frank's job was to put together an agenda for the meeting that included Carl Sagan and Barney Oliver and Otto Struve and several other individuals. They met at the Green Bank Observatory in West Virginia in a little conference room. Frank, in coming up with the agenda, thought, well, SETI makes sense if there's a reasonable assumption that there are, in fact, large numbers of advanced technological civilizations out there. And let's call that number N.
Okay.
But then how do we possibly guess or calculate how big N is? And so he thought, well, there's a series of questions we'd want to ask and answer to sort of come up with a framework to scope out how large N is. And he felt that the first one was, what is the birth rate of stars? What is the cycle of life over which stars exist, which are where planets come from, and the energy source for life. So pretty central to the question. And next he said, well, okay, now if we know something about the birth rate of stars, how many of those stars have planets? What fraction of them have planets? And if there are stars with planets, and remember in 1961,
we didn't
know. If there are any, how many of them are potentially habitable environments? They're the right size, they're the right distance from their host star to potentially have liquid water on the surface, but also, hard surface on which life can pool and form. And then if life happens, in how many cases do evolutionary processes have a chance for complex and intelligent life to emerge?
The great filter.
What is there one, or does that happen? Is it common? Is it rare? And then if intelligence emerges, in how many other cases ultimately will a technological species emerge from that whose behaviors would be potentially observable from great distances? And if technology emerges, if an advanced civilization emerges, then how long do they remain detectable? Not how long do they last. He was careful about that, but that's one of the implications.
Right.
But how long do they remain detectable before they either disappear for whatever reason, self-made or natural phenomena, or they evolve into something no longer using technology in a way that we can observe?
Dune.
A dune, yeah,
They're not allowed to use technology anymore.
Yeah. I think it was Arthur C. Clarke who famously said, a sufficiently advanced technology will be indistinguishable from magic. Another perspective on that same phrase is, a sufficiently advanced civilization may be indistinguishable from nature.
Yeah.
So all of these questions were translated into variables, and if you string them all together and multiply them together, they would give you some estimate of N. So N equals R star, birth rate of stars, times F sub P, how many have planets, times N sub B, how many of those are habitable, times F sub L, how many have life, times F sub I, how many have intelligence, times F sub C, how many have communications technology, times L.
I love how you have that fully memorized.
Oh, yeah. It's like embedded. And it's really interesting because, Frank, of course, I mean, he had no idea. I mean, literally, this was putting together an agenda for a meeting.
Yeah, it was a thought process.
It was a
right?
thought
It's a
process.
framework, yeah.
And exactly. And he had no idea what would happen to this equation and it would become so famous. And
There's a neon sign out there.
And it's on
He
a
had no
neon
idea.
sign in our lobby. So there you go. Frank was, I think, quite prescient in many ways because his own perspective on the equation was it's the only thing that matters is L. He was convinced, even in 1960, that planets are going to be everywhere. Life is going to happen a lot. Intelligence will emerge, and in some cases, technology will emerge, and it's all going to depend, if we can find them or not, on how long they last or how long they may remain detectable. His license plate, he had a vanity plate in his car, was the letter N, followed by the letters E, Q, L, S, L. So it was N equals L. How cool is that?
I love that so much. Like back in the 60s too. What has changed in the last 40 years to keep us like searching for life, right? Like
Sure.
what we haven't given up, right? So there's got to be something that like we keep finding new things. What has changed in the last 40 years?
So I think there's several things have changed. In the first, say, 20 years at least, it was a very minimally funded endeavor with small amounts of technology, looking at very small parts of the electromagnetic spectrum, which is like just a guess. Well, where should we look? They might be transmitting blue or green or orange or yellow. Which of these colors do we look for, right?
Right.
And same in the radio spectrum. What frequencies do we look for and what do we have the capability to look for? And how much information can we process and how many parts of the sky can we look at?
Right.
Jill Tarter famously described the endeavor as, shrink the cosmos into the oceans of the world. If you want to know how much of the oceans of the world we've looked at, and from a SETI perspective, go and stick a measuring cup in the water and take it out. And that's what we've looked at. And she said, if you saw no fish in that cup, you would be very wrong to, come to the conclusion that there's no fish. But that's, so, that's been the equivalent. I would say what's happened in the last 20 years, and almost even more specifically the last 10, technology has changed dramatically with the invention of faster, microprocessors and chips, and now the GPU, and just signal processing power, the sensitivity of instruments and detectors, the number of telescopes that there are that are doing this kind of work, how much of the spectrum we can look at, how far we can look. We can look at 1 million stars in a fairly short period of time within a year that would otherwise have taken like decades with modern technology. So we have a lot more technology deployed, and therefore, we're able to make that measuring cup maybe the size of a pail or thereabouts. We now know there's other things to look for. And this is the other interesting thing. As we understand more about the natural world and various phenomena like lasers and radio and so forth, there may be other things. Do we ever have an argument that says we should look at neutrinos for possible ET signs, or, gamma rays, or, what else? What have we yet to discover that provides another mode of inquiry for us to investigate? So we now also look for laser pulses and laser transmissions with the laser SETI program. So all of these things really translate to sort of an exponential increase in the amount of resources applied to this problem or this question. And still, these are very minimal, but a huge increase. I would say the most other and truly profound thing that's happened in the last 20 years, again, let alone the last 40, is the discovery of the ubiquity of exoplanets. Thanks to Didier Queloz and Michel Mayor, who made the discovery of the first big planets using radial velocity method and got the Nobel Prize in physics in 2019 for that discovery. But then more profoundly, the subsequent Kepler mission by NASA, right here at NASA Ames under Bill Barucki, that discovered planets are ubiquitous, that every star in the sky is a solar system, which is a neat thing. It's great to go out on a beautiful starry night with, a friend and say, you see all those stars up there, those are actually solar systems. And then be like, what? What are you talking about?
And they could have life.
Yeah, and they could have life.
Somewhere.
Absolutely. And so I think that is a truly profound, game-changing discovery. And it, forever changes our perspective of humanity's place in the cosmos, just as Copernicus changed our perspective when he told us it was the Earth going around the sun, not the other way around. But a profound shift in our comprehension of our standing in the universe, and also this profound transformative moment in SETI where it says, the stuff we were looking for, there are targets out there. There are loads of them.
Right.
And like billions of them, tens of billions of them in our own galaxy are potentially habitable. I mean, that's
crazy.
It's crazy. That's crazy.
Yeah, it's the famous quote, right? If it's just us, it's an awful waste of space.
It's just big. I mean, Sagan was full of such brilliant, beautifully phrased quips, and I wish I had half his ability.
Without ChatGPT.
Right. Yeah. And but he could put something very succinct out there that was profound and its implications, and it's so true. I mean, the scale of the universe is beyond our ability to comprehend it. I mean, the closest star, Alpha Centauri, at 4.2 light years away, would take us, with our current technology, 18,000 years to get to. And then, that's right here next door to us in a galaxy of 300 billion stars, which is one of hundreds of billions of galaxies, each one separated by roughly 1 million light years. I mean, the scale, we can't grasp it. So yes, the idea that this would be the only place and that huge parameter space that life occurred is kind of nuts.
So looking forward to the next 20, 40 years, what are you most excited for?
I have kind of, I would say, sort of parallel paths of excitement, if you will, and interest, because the endeavors are of course connected, but they're separate. And that is the search for life, even in its most basic form, even right here in our own solar system, and then SETI. We may be within a couple of decades of discovering either extinct or extant life in our own solar system. And it could be on Mars, it could be on Titan or Europa. What's really interesting is, if we look at these worlds beyond Mars, where it hasn't been possible for there to be an exchange of material between Earth and these bodies, like there is between Earth and Mars, if we find life on an environment like that with a clearly unique biogenesis, I mean, that's also game-changing, because that would say, okay, life is happening like wherever it possibly can, wherever the basic building blocks, it's going to happen. So it's going to be everywhere. I mean, my own perspective on this is the most remarkable thing we may discover about life is that it's not remarkable at all.
Yeah.
And you can quote me on that. I'm hoping to be famous for that quote someday.
I love that.
But I'm dead and gone. But in any case, I honestly think that's true. So I'm very excited about, the search for life and a better understanding of the origins of life. We don't even have a working definition for what life is, right? But I think that the discovery of life elsewhere in our solar system and potentially, separate biogenesis life is very likely in the next couple of decades. That may just barely give me enough time to witness that. And SETI is the kind of thing where, it could happen tomorrow, or it might happen in 100 years, or it might happen in 1,000, or it might never happen. But the one thing that I also love about that endeavor is the probability of finding life beyond Earth, if you don't look for it, is zero. The more technology we apply to it, the more instruments, the more places, the more, other nations and observatories and so forth that get interested and excited about this, and that's happening all over the world now, the more likely we are to make a discovery.
And just like how much has changed in the last 10 years. And I think we all see that in our day-to-day lives, like the integration of AI just in 2 years or something.
Unbelievable, right?
And, cell phones and cameras and everything. Like I can't even fathom what is going to happen in the next 10 years. I don't think really any of us can, let alone 40.
That's right.
And I'm really excited to see that, integration of new technology into SETI and getting people excited about it. And that's where the education comes in, getting more scientists involved and things like that.
Well, here's an interesting 40-year perspective, okay? So the Institute was founded in 1984. So roll the clock back 40 years before that. It's 1944. In 1944, human technology passed the Kármán line into space for the very first time.
Wow, exactly 40 years.
40 years before, exactly 40 years before. Yeah, sadly, that was a B-2 rocket, which was designed as a weapon, but nevertheless, a human technology went into space in 1944. Roll the clock back another 40 years. It's 1904. In December of 1903, the first flight was made by a human-powered flight, right? I mean, that's amazing. So you went from powered flight, 40 years, rocket into space, 40 years, people doing SETI. And actually, in between the SETI Institute being discovered and 1944, you had humans walking on the moon. And can you imagine walking up to a random person? Can you imagine interviewing somebody in 1944 and saying, so, what do you think about 25 years from now, people walking on the moon, right?
They would think you're crazy.
You're crazy. They would literally have said, lock her up. Really, right? So in that same vein, what can we imagine? I think we're just not able to imagine, what will be happening 20 to 40 years from now, because it will be, so mind-blowing compared to what we now understand. that it'll just be too far beyond us to comprehend.
I love it. I think we'll end on that. Thank you so much
You're
for
very
your
welcome.
time today.
Yeah.
It's great to chat
Nice
with you.
talking to you. Loved it.